So as you probably know well, when you do a single test using a standard null hypothesis significance testing approach, and for example, you use a 0.05 alpha criterion, what you're saying is that you're accepting a 5% chance that the value you find, although it appears to be extreme, actually still comes from the null, from the far tail of the null distribution. In other words, you're accepting that you have, in this case, a 5% chance of incorrectly rejecting the null hypothesis, which results in a false positive. And as I said, when you do one test, we accept that the chance of having such a false positive is 5%. But when we're doing fMRI, we're doing what I referred to in the past as a massive univariate approach, which means we are testing at the same times, hundreds of thousands of voxels all in parallel. So if you think of it this way, then if we do, if we do several tests, for example, if we do 100 tests, and if each of these is at 0.05, this means that overall, I'm likely to reject the null hypothesis, five times just out of chance. And that's what you're seeing right here. In fact, in this particular data set, so these are just null data, randomly drawn from a distribution with mean 0. And just by chance, every now and then, there happens to be some extreme values that were above threshold. And as I said, this data was a pure null simulation, so there was actually no effect in there. But just by chance, there will be a few times where, if you add sort of the noise will just be strong enough that it will be above threshold. And so you can see just by doing 100 tests in parallel, we're already getting 5, well, in this case, 6 false positives. So imagine doing exactly the same on 100 to 200,000 voxels, which is more or less the space of fMRI data. So this is another example of this issue, which was done by my friend Jonathan Peel. So what you're seeing here is a thresholded fMRI image, and the image was thresholded in a fairly lenient way. It was thresholded by imposing that each voxel has to meet the 0.05 criterion, but then we also need to have little clumps of at least 20 voxels, right? So this is sort of the type of thresholding that was done to this image. And you can notice that there are some areas of activation, for example, right here in the anterior temporal lobe, in the superior temporal gyrus, some in the motor cortex. And in particular, my friend Jonathan, he's really interested in auditory processes. So these areas right here, superior temporal gyrus, anterior temporal lobe, they are and also some of these posterior temporal right here. These are all areas that are very relevant to auditory processing. So these are all areas that if they were active in your study, in fact, in one of his studies, he'd be very interested by and would be consistent with what he did, with what he studies. The problem, however, is that the way in which he generated these data is by creating completely null data, meaning he created a Gaussian distribution. He assigned every voxel a number that was taken from a Gaussian distribution with mean 0. So complete null hypothesis, and you can see this on the left. These are just noise data. And then what he did is he smoothed these random data, much like we do in our pre-processing analysis. And in fact, he even commented in the slide on how surprisingly these data really do look a lot like processed fMRI data. And in the previous lab, I've asked you to keep opening up and looking at these data so you know what they look like. And so just taking noise voxels and smoothing them, you get this. And if you then threshold them using the thresholds that I mentioned earlier, you actually get some significant results. So this is just a way of emphasizing that when we do parallel tests on the scale that we do with fMRI data. Again, it depends on the resolution of your data set, but it can be anywhere from 100,000 to 200,000 voxels. So when you do that many parallel tests, it is clear that you will end up with a lot of false positives. So we need to address this. Now, if you want to put this in sort of a more formal way, when you do one test, as we said, what is the probability of getting a false positive? Well, that's what we set, right? Generally 5%, and we just accept that, that possibility. Now, if we make two tests, what is the overall probability across the whole family of tests, so across both tests, that at least one of them is a false positive? Well, that turns out to be a simple calculation. That is 1 minus alpha to the power of 2. So at the nominal 0.05, if each test is at 0.05, then as a family, those two tests together, the chances of getting at least a false positive is 9.75%. And of course, you can keep going and you can generalize this by saying, well, if I make n tests, what is the overall probability as a family across all the n tests that I'm doing of getting at least one false positive? Well, it's 1 minus alpha to the n. So now think of it in terms of how many tests we do in fMRI. As I said, images vary and it depends on the resolution of your data. But generally, data sets can vary and can be between 100,000 to 200,000 voxels. Now, compare this to how many comparisons it takes to ensure that you get at least one false positive. So these various curves, so here I'm showing on the x-axis the number of comparisons going from 0 to 1,000. On the y-axis, I'm showing what is the probability of getting at least one false positive. So the blue line is if you use 0.05 as a criterion, then by the time you do 100 comparisons or a little more, maybe 150, you're guaranteed to have at least one false positive. Guaranteed. If you use a slightly more stringent threshold, if you use 0.01, then you have to get to about 600 comparisons before you are guaranteed to have a false positive. And if you use 0.005, then you have to get close to 1,000 comparisons before you're guaranteed to have a false positive in your data, in your results. And of course, as you make the threshold more stringent, it takes more and more comparisons to be guaranteed to have at least one false positive in your results. But again, our scale is massively above any of this. Our scale is 100,000 voxels. You're guaranteed 100% that you will get false positives at this scale. So let's just assume that our image has 100,000 null voxels. There's no effect in there. There's no significant, there's no real effect in there. But just by virtue of doing 100,000 tests and by having noise in our data, how many times will we incorrectly reject H0? In other words, how many false positives are we going to have? Well, at the nominal alpha of 0.05 per test, we're talking about somewhere around 5,000 voxels. So just by chance, just because we're testing so many voxels, we will have a large number of them that will be positive just by chance, that are all false positives. And see, this point was made sort of very cutely in an experiment a few years ago now, titled Neural Correlates of Interspecies Perspective Taking. Now, here's what happened. The stimuli in this experiment were pictures of faces, some of which had emotions and some did not have emotional expressions, or at least didn't have obvious emotional expression. The task was to look at these pictures and try to determine the emotions that were being experienced by the individuals depicted. And it was a very simple block design. So, block, rest, activation, rest, activation, rest. And the analysis was a completely standard analysis. In this case, it just happened to be done with SPM, but exactly the same analysis that you and I would do on data. Now, what is strange about the study is that the subject was one dead Atlantic salmon. And even if it were alive, it would be hard to make a case that it would be able to understand your instructions and then comply with them, and all the less be able to recognize any emotional expression. And on top of it, anyway, it was dead. What is interesting is that if you do the full analysis pipeline, turns out you get significant voxels, which you're seeing right here for the task. Now, of course, this is because they hadn't corrected for multiple comparisons. So even, right, so this sort of, in a sense, this is sort of a toy example, but makes a very strong point. It's really key to correct for multiple comparisons. Else, you're going to end up with activations, and the problem is that you are going to risk interpreting activations that are complete noise. Just like the example that I gave at the very beginning, just because by chance there were activations in parts of the brain that typically make sense for the studies that my friend Jonathan Peel does expose him to the risk that if he does get, just by chance, some noise activity, some false positives in those areas, he might venture into interpretations of what it means. If you didn't know the whole, the game behind this, you would see activations there, and you say, oh, this participant is, is responding to the emotional phases, and this part of the brain is the one that is important for emotional responses. Now, if we put this at the scale of the human brain, for example, this image has somewhere close to 30, just this slice has somewhere close to 34,000 voxels. So if you use a 0.05 criterion, then you get, in this particular case, just about 1,600 voxels that are significant just by chance. These are all false positives. There's no signal in these images. Of course, if you make as you'd expect, if you make the criterions more stringent, if you do 0.01, you only get 364 voxels active just by chance. And if you do it even more stringent, you get even fewer. But it's clear, just imagine that just by chance, some of these voxels that are active were to clump somewhere around here. You might see that and mistake it for a real activation and venture into all sorts of interpretations about why that particular piece of the brain is active in your task, even though it's exclusively false positives. Now, of course, this also leads us to the issue of, well, but how much correction do we need to apply to our images? And this is a difficult problem. It's a difficult problem because it's a bit of a delicate balance. Achieving the right correction is a delicate dance, trying to trade off specificity and power, because you always find yourself in a trade-off between these two. Let me show you what I mean. On the one hand, if you correct very little, you're going to have very good power. Anything that is even remotely related to your task will be significant. On the other hand, you're also going to get a lot of noise. You're also going to get a lot of false positives. And if you look at the image, you have overall very poor specificity, meaning if I were to look at this image and you were to ask me, but okay, so where is this task represented in the brain? I would look at this and I'd say, well, gee, kind of everywhere, right? So I have very poor specificity. On the other hand, if you're really to crank up the dial and correct very harshly, we'd find ourselves exactly at the opposite end of the spectrum. So we would have excellent specificity. I can tell you, look, this task activates exactly this part of the brain, this part of the brain, that part of the brain. That's it. However, we also have very, very bad power. meaning there's probably a lot of voxels that might have been related to the task, but because our correction was so strong, they're now false negatives. So see, we really find ourselves in between this delicate balance between, good specificity and good power. And so it's crucial to try to find what is a good middle between these corrections, although I admit it's very hard to do.